Good day to our lecturer, Dr. Rozumi. This is our modern control system mini project. Our title is Aircraft Autopilot Control System. Our group member is BENG FOOK, Lai Jiawei, Lim Chun Tat, and Yip Ding Hui. I am Yip Ding Hui. First, I will discuss about introduction of Aircraft Autopilot Control System. An unmanned aerial vehicle UAV is an aircraft, often a fixed-wing airplane, which can operate under its own control or under the control of a remote human pilot. North American Robotics (NAR) has been developing UAVs with special camera and sensors for scientific environmental research projects, precision agriculture and improved farm production, real estate properties inspection, municipal site management, and emergency response support. An unmanned aircraft system UAS include the UAV and a ground control station GCS of some form, along with a telemetry communication channel between the pilot, the UAV, and the GCS. The smart pod is attached to the strongest areas of the host aircraft to create the rugged UAV. It is shaped to be aerodynamic to serve as an effective landing sled to protect the instruments and the aircraft. Smart pod UAS is a system that consists of prior hot UAV, ground control system GCS, and transmitted spectrum DX7 or DX8. Prior hot UAV is RC power greater but become workhorse UAVs after some ruggedizing and the attachment of the smart pod with the avionics. The ground control station can be any of a variety of notebook PCS brought to the field in the ruggedized Pelican case. The GCS communicates with the UAV through the 900 MHz transceiver. Mission Planner is software running on GCS. All flight data is touch recorded on the GCS using the Mission Planner. Inside the Mission Planner, the UAV pilot can see a satellite map or drawing of the area they plan to fly. Transmitter is the overriding control between the UAV pilot and the GCS or UAV. The switch on the transmitter will be pre-programmed and allow the UAV pilot to switch between flight modes.
Hello, I am Lim Chun Tat from RK20. This is the question for our mini project. A high-performance jet aircraft with an autopilot control system with unity feedback is shown below. So we have the autopilot parts and aircraft dynamics parts. So for the question, we have part A and part B. For the part A, we need to draw a boat plot of the system and determine the gain and phase margin of the system. So assume the K equal to 50 in the equation given just now. So what is the boat plot? Boat plot is a graph of the frequency response of a system. It's usually a combination of both magnitude plot expressing the magnitude in dB, which is decibels, of the frequency response, and a both phase plot expressing the phase shift. So what is the gain margin? The gain margin is the reciprocal of magnitudes at the phase crossover frequency. The greater the gain margin, the greater will be the stability of the system. This refers to the amount of gain which can be increased or decreased without making the system unstable. It is usually expressed in dB, which is decibels. For the phase margin, amount of Additional phase lag at the gain crossover frequency required to make the phase angle of the open loop frequency transfer function equal to negative 180 degree. So for the same as the gain margin, phase margin also, the greater the phase margin, the greater the stability of the system. It refers to the phase which can be increased or decreased without making the system unstable. It usually expressed in phase.
Hello, my name is FOOK. So the question A is to draw the dot plot of the system and determine the gain and phase margin of the system, assuming the K is equal to 50. So first of all, we need to expand the equation. So the expanded equation is K and the bracket of S plus 5 over S cubed plus 9 S squared plus 14S. As you can see, the left hand side is the syntax and the right hand side is the graph. So S is assigned to equal to a polynomial, and then we insert the open transfer function we calculated just now into the syntax, into a numerator and a denominator. The numerator is equal to 50 times S plus 250, and the denominator is S cubed plus 9 S squared plus 14S. And then the variable TF is the transfer function, is assigned to the continuous linear system. And the syntax show margin transfer function is to show the margins on the graph. So at the right hand side, as you can see here, the phase margin is about 1.01 Hertz or 6.3 radian per second. And it shows the phase margin is about 26.94728. And in this region is the positive region. It means it's always stable. And the gain margin is infinite, because the total phase shift tends to be exactly 180 as the frequency tends to infinity at which point the transfer gain is infinite. So the system never becomes unstable no matter how much gain we keep on increasing. The question B is about you are required to design a compensator, either leak or lag, so that the phase margin will be at least 40 degrees. Produce your design. So the general compensation network consists of a function about S plus Z over S plus P, which the Z is the 0 and the P is equal to pole. The compensation network is called phase lead compensation network if the absolute of Z less than the absolute of pole. In some books, the transfer function of phase lead network also written as 1 plus alpha tau s over 1 plus tau s. Because the 0 first on the frequency axis, we obtain a phase lead characteristic as shown in the following figures. As you can see, the phi max is equal to arc size alpha minus 1 over alpha plus 1, and the crossover frequency is equal to 1 over tau square root of alpha radian per second.
Hello, it's me again, Lim Chun Tat from RK20. Since we are using phase lead network to design our compensator in part B, so by adding a phase lead network to our system, we can increase our phase margin by V max if we choose omega m value, which is similar to the gain crossover frequency. However, since there is an addition to the gains as well, we have to expect our gain crossover frequency increase a bit in order to overcome this problem at a safety margin around 15 degrees to our required phase margin. For guidelines in designing phase lead network in part B for this question, first one is find the system phase margin PM and gain crossover frequency. Second one, find the V max which is the required addition for phase margin and add safety margin, which is Vmax equal to phase margin needed, which is also equal to phase margin required minus phase margin current. After that, add 15 degree. The third one is solve for alpha. The fourth one is use alpha value in omega m formula, where omega m equal to gain crossover frequency, and solve for tau. The fifth and which is the last one, rewrite the lead network transfer function in this form: GCS equal to 1 plus alpha tau s over 1 plus tau s.
Hello, I'm Lai Jiaowei from RK20. Now I will present the solution for question B. From the result of part A, the phase margin obtained is 26.94 degree, and the gain crossover frequency is equal to 1.172 Hz, and which is equal to 6.3913 radian per second. This is because 1 Hz is equal to 2 pi radian per second. Now, the Vmax is equal to phase margin needed, and which is equal to phase margin required minus phase margin current, which is 40 degree minus 26.94 degree, and we will add 50 degree. This is because the safety margin, and the result is 28.06 degree. By using the Vmax, which is equal to inverse of psi alpha minus 1 over alpha minus plus 1 equal to 28.06, we can obtain the alpha, which is equal to 2.7764 by doing the calculation. And now, next, we will solve for tau. We can obtain it by using the gain cross frequency formula, which is equal to omega m equal to 1 over tau square root alpha, and it is equal to 6.3913. And doing the calculation and the exchange, the tau obtained is 0.0939. Then we can rewrite the lead network function into the general form, which is 1 plus alpha tau s over 1 plus tau s, and the result is 1 plus 0.2607 s over 1 plus 0.0939 s. And we can get the phase margin by using Scilab, and the left side is the syntax. You can see that the transfer function is equal to lead function times the original transfer function. And by using the syntax show margin, we can get the graph. You can show this. This is the frequency is 1.4936382, and the phase margin is equal to 47.082745. This fulfill the requirement of compensator of phase margin would be at least 40 degree. That's all.